Peggy 3.
In this video, we aim to introduce the basic concept of coordination chemistry. The objective of this video are to explain what coordination compounds are, to describe the meaning of coordination number, to outline the common type of geometries found in coordination compound, and to introduce the basic idea of isomerism in coordination compounds. Introduction. Coordination compound are chemical species that consist of a central metal ion surrounded by ligand. These ligand donate electron pair to the metal ion, forming what is known as coordination sphere. This coordination compound may be neutral or charged, and when the complex is charged, it is stabilized by surrounding counter ion. The overall gravity of coordination compound depend on the type of metal ion present, as well as the number and the nature of the ligand attached to it. Coordination compounds are very important because they are widely used in many fields such as medicine, catalysts, and material science due to their unique chemical properties. For example, a platinum-based coordination compound are used in chemotherapy for cancer treatment, where they play an important role in modern medicine. This introduction provides a foundation for understanding how coordination compounds behave, which will be further explained through coordination number, geometry, and isomerism in the following section.
Coordination number is defined as the number of ligands, typically non-metal compounds, that are attached to central atoms. As per an article from LiberText of 2023, central atoms are typically transition metals. As per an article from LiberText of 2023, there are three types of ligands, namely monodentate, bidentate, and polydentate ligands. Monodentate translates to one tooth, and ligands bind to one central atom. A basic example of a monodentate is water, which is known as aqua ligand. Bidentate ligands bind to two donor atoms, which are connected to one central atom via the availability of free electrons. A basic example is ethylene diamine, where there are two amine donor atoms. Polydentate ligands bind to multiple donor atoms, and ambidentates can bind to donor atoms in two areas, such as thiocyanates, where the ligands can be found in either sulfur or nitrogen donor atoms. Counter ions do not count as part of coordination number due to being a component that simply balances out the charge of central atoms and are written as outside of the parentheses where the central atoms and ligands are within the chemical formula. According to an article from LiberText of 2023, common geometries are shapes that a chemical compound would crystallize into. These shapes are determined by the ligand's binding orientation, but are not necessarily bound by the number of ligands that are attached to the central atom. The coordination number of these geometries can be up to 16. However, for the sake of brevity, we will only focus on three values, which are coordination numbers 2, 4, and 6. Our first entry of common geometries will be for coordination number 2. The shapes for this geometry are typically linear, where two ligands are 180 degrees from each other from the central atom. Appearances for this geometry are uncommon for first-row transition metals. Examples of coordination number 2 geometry compounds are diamond silver 1 cation with 2 ammonia ligands. The second entry for common geometries would be for coordination number 4. The shapes for this geometry are either tetrahedral or square planar. Tetrahedral geometries are the most common geometry, with ligands attaching to a central atom at 109.5 degrees of each other. One example of a tetrahedral compound is nickel tetracarbonyl with 4 carbonyl ligands. Square planar compounds are the least common geometry of coordination number 4, with appearances only in D8 electronic configuration and ligands attaching to a central atom at 90 degrees of each other. One example of a square planar compound is tetrachloroplatinate 2 ion with 4 chloride ligands attached to a platinum central atom. The third and final entry of our common geometries would be for coordination number 6. The shapes for this geometry are either hexagonal planar, octahedral, or trigonal prism. Hexagonal planar compounds are unknown or not available for first-row transition metals, with ligands attaching to a central atom at 60 degrees of each other. Trigonal prism compounds have three bidentate or paired ligands, with the ligands attaching to a central atom at 60 degrees base angle and 90 degrees base to side angle. One example of a trigonal prism compound is the hexametal tungsten with 6 metal groups as ligands. Octahedral geometry is the most common for coordination number 6, with ligands at 90 degrees adjacent at 180 degrees at opposite sides of each other. An example of octahedral compound is hexacyanoferrate 2 ion with 6 cyano groups attaching to iron, according to an article from Kaup of 1996.
Next, I will discuss cis-trans isomerism, which is a type of geometrical isomerism commonly found in coordination compounds. Cis-trans isomerism occurs when ligands are arranged differently around a central metal ion, resulting in compounds with the same molecular formula but different spatial arrangements. These different arrangements lead to distinct physical and chemical properties. For example, square planar and octahedral complexes. In square planar complexes, such as those with coordination number 4, cis-trans isomerism arises when two identical ligands are positioned either on the adjacent to each other, which is cis, or opposite to each other, which is trans. Similarly, in octahedral complexes, which have 6 ligands around the metal center, cis-trans isomerism occurs when two identical ligands are either next to each other or directly opposite across the metal ion. Even though the chemical composition remains the same, the difference in geometry can significantly affect properties such as reactivity, polarity, and biological activity. In addition to geometrical isomerism, another important type of stereoisomerism is optical isomers. Optical isomers exist as non-superimposable mirror images, also known as enantiomers. This occurs when a coordination complex lacks a plane of symmetry, making it chiral. Optical isomerism is particularly important in biological and pharmaceutical applications, as different enantiomers of the same compound can interact very differently with biological systems, sometimes resulting in beneficial effects or harmful side effects. In conclusion, cis-trans isomerism arises from different ligand arrangements in square planar and octahedral complexes, while optical isomerism involves non-superimposable mirror images of chiral complexes. These forms of isomerisms highlight the importance of molecular geometry in coordination chemistry, as even small changes in spatial arrangement can lead to significant differences in chemical behavior and real-world applications. Understanding geometry and isomerism is therefore essential for explaining the structure, properties, and functions of coordination compounds. That's all from me and from my group. Thank you.